everyone. So this is another live session for Math1055. I believe it's number 10. So as always, feel free to ask questions using the chat, and we'll go through problems related to this week's videos. But before we do that, let's just start with this problem. So as usual, you can go to this webpage, itempool.com/math1055/live, and here is your first question. So it's asking you to compute this expression. So you have three vectors in 3D space given to you, and you have to compute the cross product of the first two vectors, and then the dot product of the third vector with the cross product of the first two. So vector A is expressed in the usual basis using the usual basis vectors as 2i plus j, 2i hat plus j hat minus k hat. Vector B is minus 5i plus 3k, and vector C is I minus 2j plus k. So this way you have the coordinates of each vector, and you are asked to calculate A cross B and then the scalar product of A cross B with C. Okay, this is just to see if you all have it sort of nail down the cross product, dot product, vector product, scalar product kind of calculations. So you can go to itempool.com/maths1055/live once you have calculated the answer. Well, let me just tell you in advance that the answer should be a single number. So there is the box where you can enter your answer. So if you go to itempool.com, to this web address, there should be this input box in which you can submit your answer, and it should be a number. Okay, and you might be thinking, what a strange thing to calculate, A cross B dot C. Does it have anything to do with, you know, geometry, or what does it tell us, this number? Well, I'll tell you in a second, but I want to give you another minute or two to finish your calculations. Do let me know if you need more time. Let's say I'm going to give you another minute and then finish this poll. But if you would need more time, if you feel like you're almost there, you just need a minute, I'm happy to give you that. But we'll go through the calculations, the calculation together, and we'll see what's the answer and how it's related to geometry. Yes, so this is a known issue. Thank you, Adam. So Adam has written in the chat that there was this issue with the item pool that are sort of connected to the lecture videos. So this week's videos, there were certain questions where I asked for the equations of lines, and for some reason it didn't want to accept the correct answers. It sort of flagged them as wrong, even though in the video you could see that what the correct answers were, and you might have inputted those. So that was a glitch on item pool's side. I tried to fix these questions, so now you have to input your answer coordinate by coordinate. It seems to work this way. It used to work the other way, but for some reason it broke. So hopefully, if you look at the videos again, they should be fine now. These interactive elements. Okay, so let me finish the poll and reveal the answer. Let's see if okay, so most people got it right. There are some different answers. So the correct answer was 10, and let's see how it's done. So how we calculate this certain combination of vectors, this product of vectors. So first we want to go ahead and calculate the cross product, the vector product of A and B. And remember, that's basically nothing but a a 3 by 3 determinant with the basis vectors being in the first row, vector A, the coordinates of vector A in this basis are written in the second row, and the coordinates of vector B are written in the third row. And if you expand this determinant in the first row, what you will get is basically this linear combination of I hat, j hat, and k hat with alternating sign and with these 2 by 2 determinants. So the way you read off those determinants is for each vector. So for I hat, you cover its row and column, and you look at the 2 by 2 determinant that is left, that you can still see. So it's 1, -1, 0, and 3. 1, -1, 0, and 3 for I hat. So remember, for j hat, we have this minus sign in front of the determinant. So if you cover the row and column of j hat, you are left with 2, -1, -5, and 3. So 2, -1, -5, and 3. And finally, for k hat, you get the 2 by 2 determinant that is 2, 1, 5, and 0. So 2, 1, that is -5 and 0. And all you have to do now is just to calculate these 2 by 2, these smaller determinants. And that's just done by multiplying the diagonal elements and subtracting the product of the off-diagonal elements. So in our case, it's 1 times 3 minus 0 times -1 is the coefficient of I hat. Then we have minus 2 times 3 minus -5 times -1 for the coefficient of j hat. And we have 2 times 0 minus -5 times 1 for the coefficient of k hat. So what we get is 3 I hat for the first component. Then we have minus, well, let's see what we have in the parentheses. We have 6 minus +5. So 6 minus 5, that's 1. So that's -1 j hat. And finally, we have 0 minus -5. So that's +5 for the coefficient of k hat. Okay, so I hope this was so far so good and easy to follow. So now we have the cross product of A and B. So this vector that we get by taking the vector product has coordinates 3, -1, and 5. And if we take, now remember we had this, so this was A cross B, and we had the vector C given by its coordinates as 1, -2, and 1. So, and we were interested in the vector, the scalar product of A cross B and C. So if we multiply the first coordinates, the second coordinates, and the third coordinates, and then add these products up, we should get our answer. So we have 3 plus 2 plus 5, giving us 10. So this is indeed what the correct answer was. So 10 for this combination of products of vectors. So first we take the vector product and then the scalar product with the third vector. So as I said, you might be wondering what this number really is. Does it have any geometric meaning? And the answer is yes, it does. So let me show you on the next page. So if you have 3 vectors, let me try to sketch this out. If you have three vectors in 3D space, so here I have vector A, then we had vector B, let's say it's like so, and vector C. So imagine this is in 3D space. We have these three vectors pointing in some directions. So first, what we have is this vector product of A and B giving us this vector that's perpendicular to both A and B. And the point is that if you take the scalar product of A cross B and C, what you are really getting is the volume, the signed volume of this parallelepiped that is spanned by these three vectors. So you can imagine that there is this sort of rectangular, sort of brick-like thing in 3D space spanned by these three vectors. Of course, you know by now that this parallelogram on the bottom has an area that is the length of A cross B, and the volume of this parallelepiped is base times height, the area of the base times height. And if this angle here is theta, then what we are basically getting here when we calculate this scalar product of A cross B and C is the area of the parallelogram on the bottom multiplied by the length of C times the cosine of theta. And that's nothing but really sort of the projection of C to this line that is perpendicular to the base. So basically, this length here is the length of C times the cosine of theta. Well, in absolute value, really. So this number here can be negative. So let's take the absolute value. If we do that, that's done by taking the absolute value of the cosine. So this is area of the base, sort of the parallelogram that is on the bottom right there, and it's multiplied by this thing, which is the height of this parallelepiped. So in the end, what we are getting here, if we take the absolute value, is the volume of the parallelepiped spanned by A, B, and C. Okay, so that's the geometric meaning of this triple product of A, B, and C in this way. So 10 is the volume of this parallelepiped spanned by the three vectors. All right, I hope that was clear. You can, of course, always watch the recording of the video, go back to clarify things, but you can also ask me in the chat right now. So let me go to the next question in the meantime, which asks you if these two lines intersect. So do the lines given by these equations, x, y, z equals t minus 6t plus 1, 2t minus 8, but t runs through the real numbers, and this other line with coordinates or equations x, y, z equals 3s plus 1, 2s, and 0. So do these lines intersect? Is the question. It's just a yes and no question. So it's you can always guess, but there is a way to, of course, decide for sure whether these two lines intersect. Okay, I'll give you only a minute or two because this one is easy to check, to decide. Okay, so it's interesting because the two answers, okay, now they are starting to separate. They were head-to-head for a while. This started to get worried. Okay, so there are 35 submissions so far. Feel free to go to itempool.com/math1055/live. So this address and in the chat, and answer the question: do these lines intersect or not? I'll give you another minute, and then I'll finish this poll. Okay, so I hope everyone who wanted to vote has voted. And let me finish and reveal. So the correct answer was B. No, they don't intersect. And let me quickly show you why they don't intersect. So the idea is that you have these two equations for these lines. So line 1 has coordinates, well, has points, consists of points which have coordinates x, y, z in this form, and line 2 consists of points which have coordinates x, y, z in this form. So S and T are the sort of parameters for parameterizing these lines. And if you are looking for the intersection, what you are really looking for is a point which sits on L1 and L2 at the same time. So you are looking for certain special values for T and 1, which would give you the same triple of coordinates, right? So what you are really looking for is T and S such that each coordinate matches. So the first coordinates should be equal. The second coordinates should be equal to each other, and the third coordinates should be equal to each other at the intersection point, right? So this is basically what you are trying to solve, these three equations for two unknowns, T and S. And well, there are many ways you can go about solving this, but basically from the third equation, it's easy to see that if you add 8 to both sides and divide both sides by 2, you get t equals 4 immediately. Okay, if you take and plug that in to let's say the second equation, you get, so let's number these, so 3 into the second equation, the result of 3 into the second equation, you get minus 6 times 4 plus 1 equals 2s. So from this, you get, what do you get? Minus 24 plus 1, that's minus 23. So s should be minus 23 over 2, I think. I hope I did not mess this up. So then, using this result in the first equation, we should have the following equation: t, which we've seen, we found to be 4, should be equal to 3 times minus 23 over 2 plus 1. Okay, so, and if you look at this equation, this is clearly a contradiction. So there are no two numbers. Well, this is just the right hand side is simply is not equal to 4, so that's just not true. So there is no intersection. No intersection point. Okay, so we can't satisfy all 3 equations at the same time by just finding some special values for t and s. Okay, so that was the idea. I hope that was also clear. Now the next one is a bit more difficult, I would say. The question is, what is the distance from the point P with coordinates 2, 0, minus 1 to the plane that is given by the equation 3x minus 2y plus 8z plus 1 equals 0? And we are looking for the distance from the point to this plane. Okay, so this is something that you have to think about first and then do some calculations. So if you are asking, yes, there's this question in the chat. Do you need to write down the work in progress for solving simultaneous equations, or can I simply write down the answer for it? Well, I mean, I'm assuming you're asking about sort of an exam situation or something like that. So for example, in the exam, as I told you last week, I want to see every bit of detail that you can give me about your thought process. So to be honest, I don't care about the final answer for any of the exam problems. I don't really care if you get just the final answer right, if you don't know what you are doing in the process of getting it. What I really care about is you understanding the material and these basic things that we are learning here. So what I want to see is, yes, I want to see the working out. I want to see the details. I want to see an explanation. I want to see what you are doing and why you are doing it while going and getting to the answer. Okay, so yes, I mean, this is what it's all about. It's the thought process. I want to see that you understand what you're doing, basically. And if I only see the final answer, the sort of the end result, I don't see how you got there, I might as well think that you just, I don't know, guessed or cheated or whatever, none of which is a good strategy, I would say. Okay, so let's see. There are a handful of submissions. I mean, this one is a bit more tricky, so I will just let this go on and switch to the notepad in a minute and try to explain it. And in the meantime, if you can finish your calculations on your own, that's great. Okay. So let me switch to the notepad. It's a bit too bright, but it might be okay. So here we have this point with coordinates 2, 0, and -1, and the equation for a plane. Let me try to fix the notepad view because it's a bit too bright. I think it's better this way. So it's always a good idea to try to sketch something, some sort of drawing, so you can get an idea as to how to find this distance, because now we have a plane and we have a point sticking not in the plane, and we are looking for this direction, this distance, right? We want to drop this point to the plane and measure that distance there. So of course, once you see this, basically you want this line segment to be perpendicular to the plane. The moment you realize this, that you are looking for something perpendicular to the plane, you should immediately think about the normal vector to the plane, which can be just read off of the equation of the plane. It's just the coefficients of x, y, and z if they are all on the same side of the equation. So 3, -2, and 8 is a perfectly good normal vector for our plane. Okay, so let me try to put it, I don't know, let me try to draw, let's say this is our normal vector. Okay, n. Okay, and there is p. Now, if we know the normal vector and if we know this point p, how can we cook up this distance? Well, it would be great if we knew a point, coordinates of a point on p. I don't really know. So this normal vector can be shifted parallel to each other. So I don't know if p is on the normal vector. I could take this normal vector and shift it over to q as well. It doesn't matter really where it originates from. The point is that it has a certain direction and a certain length. So this triple of points is actually giving me something that I have the origin, and from the origin it's pointing to that triple of coordinates, that point given by those triple of coordinates. Okay. So so the normal vector is definitely going to be needed in this calculation, but you can just assume that the normal vector goes through p or anything like that. So what I'm trying to draw here is the way to find this distance. So imagine that you have this normal vector, and what you are trying to do now is you want to calculate that distance from the plane to the point, and the way you do, the way to do it is to find a point on the plane. So I'm calling this Q, and the way to find, well, it's simple to find a point on the plane. All you have to do is just to pick some random x and y and solve for z. So pick some random values for x and y and solve for z. Of course, you could try to be clever about it. So for example, I see that there is 3x and 8z. Sort of, I could imagine sort of taking x to be, let's say, -3. So then I have 9 in the first term. I would take y to be 0. So this one is not there. This term can be omitted. And if I take z to be 1, then I have -9 + 8 + 1 = 0. Okay, so finding a point on the plane is very easy. You just choose some values for x and y, and you solve for z. So this is basically the same thing. I just try to be a bit clever about it. So I get some nice numbers here. So Q is a point on the plane. And now if I connect P and Q, so if I go from Q to P, and to consider this vector, now you can see where this is going, because basically this distance from the plane is nothing but the length of this vector. Okay, I could draw it over here as well, it doesn't matter. Okay, and this is something we have seen just 2 questions ago. We had this parallelepiped, and we were looking for this sort of vertical or sort of component of a vector. So QP is a vector, and we are looking for basically this component of QP. And this is the idea. So what is this component? Well, if you look at this angle and call it theta, then this component is basically the length of QP multiplied by the cosine of theta. Okay, so this length, the distance, is basically this product. Of course, the cosine of theta could be negative, so let's just take the absolute value of it, and this way we make sure that we actually get a non-negative number in distance. Again, I got Q by basically just looking for a triple of numbers that solves the equation for the plane, and I could choose any 2 values for x and y. So I could have gone, let's set them to be 0, so, and solve for z to be -1/8. Okay, in that case, 0, 0, -1/8 is just as good of a point on the plane as Q. But here I chose a different point. So anyway, so now you are seeing that this is the distance that we are looking for. So let me just write this down. QP, the length of QP, multiplied by the cosine of theta. And what is theta? Theta is the angle between the vector QP and the normal vector n. Okay, so this here is basically QP, the vector QP and n multiplied together by the scalar product. Well, I have to divide n by its length, really, because the length of n does not appear on the left-hand side. So you remember, if you remember the different definition of the scalar product, it would have the length of n on the left-hand side if I were to just write it like QP dot n. Okay, so I have to divide by the length of n, and since I wanted to take the absolute value of so a non-negative number, I took the absolute value of the cosine of theta. I should take the absolute value of this thing. So all I have to do, so this is the distance. All I have to do now is just calculate qp, the vector qp, and the length of n. Then this scalar product is the last thing I have to calculate. So first, let me quickly calculate qp. So this is just the position vectors OP and OQ. So OP minus OQ is what I have to calculate here. Let me just write. So OP is 2, 0, minus 1. So that those were the coordinates of P, and I have to subtract Q, which was minus 3, 0, and 1. So what I'm getting here is 5, 0, and minus 2. Okay, so 2 minus 3, that's 5, 0 minus 0, that's 0, and minus 1 is minus 2. So I have QP, the vector QP. Now let's look for the length of n. So the length of n, well, n is given by these coordinates. So we are looking for the length of the vector with coordinates 3, minus 2, and 8. So this is just the square root of the sum of the squares of the coordinates. So that's 3 squared plus minus 2 squared plus 8 squared. Okay, so what we are getting is 9 plus 4, that's 13, plus 64, so that's 77 under the square root. Okay, so now we have the length of n, the vector QP, n itself, so we can calculate this distance. So the distance is equal to, well, let's see. So what is the scalar product of Q and n, QP and n? We have to divide that by the length of n, take the absolute value just to be sure. Okay, so let's see. QP and n. So basically we have 15, so that's 5 times 3, plus 0, which is 0 times minus 2, plus minus 16. So this is the scalar product of QP and n, divided by the length of n, which is root 77. Take the absolute value, and you can see that the absolute value was needed because here we have, in the numerator, we have minus 1 divided by root 77. So if we take the absolute value, that's 1 over root 77. Okay, so that's the distance. Again, this was there's this question, why the cosine of theta is equal to n divided by its length. So I didn't say that cosine of theta was equal to that. All I said was that the length of the scalar product of QP and n is this fact is the length of QP, then the length of n multiplied by the cosine of theta. So all I did was just rearrange that equation. So Sam says, I don't understand how Q can be arbitrarily decided. Well, it's not arbitrarily decided, it's a point on the plane. So that was very important that Q was picked from the plane, basically. Okay, so it wasn't arbitrary. There was some arbitrariness in that which solution of this equation I picked, but from that point on, the machinery, yes. Okay, well, I mean, that is something you have to think about. Okay, so I think so the derivation did not rely on this special choice of Q, because well, you will have to, I think, rewatch the video. But the point is, we have found this distance by basically a projection of this vector QP to the normal vector n. Well, the normalized normal vector, meaning that we divided the normal vector by its length. Okay, so I hope that was clear. Well, more or less. You can always watch the video. In the meantime, I will finish and reveal the answer here. If my computer decides to, yes, cooperate. So a good number of you got it right. The sort of the correct numbers kind of are there. So let me go to the next question. So, well, I think we have already done something like this. So let me just skip to the last one right away, and we can go back, always go back to the previous one if we'll have more time. So how many intersection points do the line given by this equation and the sphere given by its equation have? So we have a line and a sphere in 3D space, and the question is, how many intersection points do they have? We could have, well, we have three options: 0, 1, and 2. So it could happen that the line and the sphere are completely disjoint, so they don't meet at all. So there are no intersection points. It could be that the line just touches the sphere, so it just sort of has one intersection point with the sphere, and it also could sort of completely go through the sphere, so go in one point and come out on another at another point, making two intersection points with the sphere. Okay, again, well, this is a question where you could just sort of make a guess, of course, but it's better if you try to do some calculations to make your guess, I guess, more educated. Okay, so I'll give you another minute or two, and then I'll finish the poll. So previously we had a similar problem where we were looking for the sort of we were trying to decide whether two lines intersected, and in that case, since we were talking about two lines in 3D space, even if you wouldn't know how to calculate that, sort of do the calculation, the more likely answer would be no, because if you just have two random lines in 3D space, they are not likely to intersect, right? They just sort of they just don't meet. It's most likely that they just don't meet. because they wouldn't even be in the same plane. So if you just picked two random lines, that is. Now here we have something different. We have a sphere and a line. Of course, again, since the sphere is kind of a bounded thing, what are the odds so that a random line just goes through it? Well, it might not be as easy to see, but again, I would say more lines miss the sphere than meet it. But of course, you can't always just guess the answer. You have to do some calculations to arrive at the correct answer. So I think I will close the poll now, just to be able to show you the answer and go through the derivation. So the correct answer was C, 2 intersection points. So most of you got it right. So again, if you just look at the line given by its equation and the sphere given by its equation, where the line intersects the sphere, we should have both equations satisfied, right? So that's the point. That is what an intersection point means. It's both on the line and the sphere. So the coordinates of an intersection point should satisfy both the line's equation and the sphere's equation. So I'm taking the components, the coordinates of points on the line, and plugging them into the equation for the sphere. So x squared plus y squared plus z squared equals 9. Gives me this combination. So if I expand everything, I get 6t squared. I get 2t from this term. I get minus 4t from that term. So that's minus 2t. Then I get plus 1 plus 4. So in total plus 5 on the left-hand side. I could bring over the 9 with subtracting 9 from both sides. So that would give me, I think, this equation. Not really, with minus 4, right? So this equation. And if I want to solve for t, I have to apply but I can just simply use the quadratic formula. So what I'm getting here is plus 2 plus or minus 2 squared. So that's 4 minus 4 times 6 times minus 4. So that's plus 4 times 6 times 4. So that's 96 divided by 2 times 6. So that's 12. Under the square root, I have 100. So the positive square root of 100 is 10. So 2 plus or minus 10 divided by 12. So indeed, I have two solutions. I have 12 over 12, so that's 1. And T2 is minus 8 over 12, so that's minus 2 over 3. That's minus 2/3. So I have 2 points of intersection. Point 1 is simply 2. Well, I'm substituting t equals 1 into the equation of the line. So I get 2, 3, and minus 1. So that's one intersection point. And the other one is minus 4/3 plus 1/3 minus 8/3. So you can check that indeed these 2 points satisfy both of these equations. And doing this last check is always a good idea to do. So I think our time is up. So let me stop here. Thank you all for attending. You were all great as usual. If you have any questions, just feel free to ask me or send me an email or anything like that.
we will have our last live stream next week, next Friday, where we'll do the sort of revision type questions. So what did I mess something up? Probably. Yeah, sorry. It should read 2 minus 1. Yes. So thank you, Adam. Okay. Take care, everyone. Have a good weekend and stay safe.